Hello and welcome to Iron Beetle, a show where we look under the hood of the Target database, a modern distributed database for counting, which is implemented in Zeek, which uses state-of-the-art deterministic simulation testing, and which doesn't allocate up the startup. So to start, first, let me apologize for starting this episode one half of an hour later, but don't blame me. Please blame Joran, who nerd sniped me about with a question about constant time code in Zeek. But we are not going to talk about constant time code in Zeek today. Maybe in some future episode. Today we are going to talk about upgrades, or rather, we actually, I think, hopefully, will finish talking about Target upgrades. Okay, so let's start with a refresher. What is Target upgrade process and why it looks the way it looks? So, problem. We want to upgrade. Problem. I don't have my screen shared. Okay. Problem. We want to upgrade Target from one version to another version. Normally, the way you would approach this problem is by making sure that your public API remains compatible between those two versions, so that for the clients, it actually is irrelevant which version of the binary is running. For Target, this approach is problematic because Target relies on the fact that on all 6 replicas in the cluster, the data files are byte for byte identical. While it is possible to maintain the public API compatible between versions, maintaining the private implementation details, which determine the specific layout of bytes on disk, is infeasible. So, Target maintains an invariant where each iteration can be processed by exactly one version of Target. And to implement zero downtime upgrades, Target actually ships several versions of Target binary inside a single Target binary. So when you download Target binary from the Target website, it is, I don't know, like a dozen megabytes, but it is a dozen megabytes because it includes 4 previous versions of Target. So actually the binary is much smaller. And there is a logic inside the database which dynamically switches from the old version on the new version for a specific op, which is a coordination point for the entire cluster to upgrade at the same time. Okay, so I think this is the third episode, the fourth actually episode we dedicate to upgrades. On the first episode, we kind of like explained the big scheme, something I've just like quickly run through at the moment, and we looked at the like build system side of things, like how we automatically download binary from a website, etc. Oh, I think we also like debugged pretty nice debug there. On the second episode, we looked at this picture, like how we actually concatenate two binaries together. As fun as it is, like you actually can like literally concatenate several binaries, and it will be able to run fine, the first binary. But you also need to inject some metadata to explain where concatenated binaries are, where one binary ends and a new binary begins. And we rely on elf file there, like we like basically pack our targetable binaries inside an elf. Finally, last week, we looked at the consensus side of thing. We learned that we want to switch operations at a particular checkpoint, and we also learned that due to the fact that checkpoints are like slightly asynchronous, we also need to part our log with no op operations, such that by the time we commit a particular checkpoint, we know that there isn't anything in flight which might depend between two versions. Okay, so today is kind of like capstone episode where we tie everything together. I think I should switch this to dark mode, where we tie everything together and where we glue this protocol level decision to upgrade to this elf file magic with actual upgrades. Okay, but before that, I want to do homework, because remember, send. Last time I said that there potentially might be a bug somewhere Okay, now I am ignore request message duplicate. There was a comment in there. Okay, yeah. So this comment kind of like felt questionable to me. I didn't actually see the case where we ignore duplicate upgrade requests, where we prevent several upgrades being sent for different versions at the same time. So this, after looking at this closer, I actually realized that, hey, this is not a bug, and yeah, so I think we actually hit this case. So there is slightly incorrect comment message here, but the code working correctly. But okay, that's kind of like not really relevant for what we're going to talk today. And today we are going to cover this release execute function. So how we actually go and execute the release. So when the protocol decides that, hey, it is the right time to do a transition, we call release execute. So release execute is a callback which is passed to us by the caller. So we actually have to look at the main to understand what is that. And here we'll be using multi-version. The physical thing which actually is responsible for two aspects. One is watching the file and noticing when operator dropped a new taggable binary in place so that we could start the upgrade. And the second is when the protocol tells us we need to upgrade, actually goes and upgrades it. Okay, so let's see. We create multi-version passing allocator, input output, and the path to the executable which is currently running. And actually it's always a fun puzzle figuring out what binary is currently running. Okay, let's see what we do here. We compute the maximum size of a multi-version binary, and we allocate memory for storing that binary. So this is a buffer where we will read the binary into when we start up. And this branching here is for max, because I think, well, actually, okay, let's not think, let's just see where we use detect. Okay, we use detect in print information. So yeah, I think on max, okay, let me actually not try to appear smarter than I am. I actually don't fully know what this logic does. I think this has to do with macOS universal binaries, like how in macOS you might merge several versions together. And okay, maybe okay, this actually makes me want to just completely get rid of this logic, but okay, that's kind of a distraction. So the main thing is we have the buffer which we can read our binary into. And then I think, yeah. What's multi-version? Okay, yeah. I think there is fundamentally we have a binary on disk. And we know that this binary is a multi-version binary. So we don't want to run this binary directly, but rather we want to execute a specific version, like subslice out of this binary. I think the way this will work on Linux, and we will learn soon, is that we actually create an in-memory file descriptor. So we essentially, you could execute file on your file system. But there is also API to execute a file given a file descriptor. So we create an executable purely in memory, and then we execute. And I think on Windows and macOS, we'll actually have to write this file to disk. And we use system temporary directory, which is kind of maybe not the right thing to do, because system temporary directory is actually world readable. So this sounds like it might be actually incorrect. Because yeah, kind of like, like in the ideal world, each user will have its own temporary directory such that only processes from this user could access it. But the global like /tmp is actually world readable. And that feels like not good. Like we shouldn't. Aha, okay. That's okay. I don't like it. So should, like, ideally we should be, well, I guess we do include, okay, again, I will not pretend that I'm smart when I'm live in Middle. I will take a look at this code afterwards. Maybe it is fine because I think we inject sufficient randomness here. But maybe not. Okay. So anyway, we have this target path. And then, okay, but why do we need a path for, okay. So apparently we still need a path, even a path on the file system, even if you create file in memory. Well, okay, it's fine. Okay, so we created this file, which is in memory, and we say that it should be whatever size it should be. Okay, and we have file descriptor, and we should not forget to close it. And okay, this is like a lot of allocation here. I don't like this at all. It feels like we might be missing some deferrers here. So let's keep our eyes peeled. Okay, for Windows, we just go and create this file and also truncate it. Okay. Wait. This is definitely not true, because we don't want like every user to go and modify this file. So this feels this feels potentially problematic. Okay, we'll take a look here. Okay, we close our file descriptor. Okay, and target path we'll close at the end, and source buffer hopefully will also close. Okay. Then what args? So presumably we want to actually re-execute ourselves with the same environment and the same path. Okay, this is curious. This is like, okay, this folks is like, real hardcore systems programming. So let's see. We copy our argument array. Okay, I bet this arg0 will be leaking. Like I am just because it here. No, it's not leaking. We actually do properly clean it up. Okay. Okay, so we set all arguments. Why are we... Well, okay. And for environment, we use... Okay. Kind of like makes sense. So we start, we have path to executable, we have args, and for starting the process, we have source buffer, where we'll be reading our file. Target FD. So target FD is like the file where we should be writing our binary. So we'll basically, source buffer is like multi-version. We'll slice a single version out of source buffer and we'll place it into target FD, I think. And then we start the timeout. Okay, when we did it, we close target FD, we free target path, we free source buffer, we free args. I think we had another file descriptor here, target FD. Well, no, there's only a single one. So target FD. Okay, yeah. Okay, as much as I want to find a resource management bug here, that seems pretty clean to me. Okay, what do we do next? Open sync. Okay, and by the way, probably makes sense to see how we initialize. So there is like a bunch of cases where we cannot initialize multi-version, and like, address 0 is one of them. We remember fixing this like a couple of days ago. But then we initialize multi-version, yeah, and then we open multi-version. Okay, so let's see. What does it mean to open multi-version? We start the source file. I think to check the stats, like, to actually notice like whether the binary was substituted. Okay, this is all horribly complicated. This is difficult. So for non-Linux things, we go and we open our own file as a binary. Okay, source FD. Do we close source FD? Okay, okay, so okay, maybe I'm fine. Maybe I have found it. So let's see. Binary open, set source FD, and okay, we are running here, and then we might return an error, but if our source FD is not empty, then okay, we'll leak in file descriptor. Okay, it's very surprising if you see Zeek code which does a lot of resource management, which actually doesn't contain this sort of bug, because yeah, it's kind of like hard to manage deferrers. Okay, so anyway, we like started the binary, and if there is some error, we just say that okay, we like still start, like we'll just we disable just the upgrades, and that makes sense because upgrades are kind of like very finicky, and like worst case operator can restart the binary themselves. So the upgrades here is like not upgrades altogether, but like just this automatic watching of what happens on disk. Okay, so and then I guess periodically, when do we say timeout start? Okay, after we open binary, we actually start ticking the replica, and then on timeout, we go and look at the binary, and source read, binary read. Okay, I kind of like okay, I'm getting lost here. Okay, so this is it feels like it's like very complicated. Okay, on timeout. So okay, let me go from the other way. What is store the multivariable? So like a bunch of stuff, and I guess the like where is yeah, so release bundled. Let's see where release bundled is updated. So like initially, when we set it, and then okay, this is all okay. So target update. So at the end of target update, we go and fetch releases from the binary which is in the source buffer, and that is the result of target upgrade. So when do we call target upgrade? Target upgrade, we call it binary read callback. So when we have read the binary, we go and do target upgrade. Okay, so let's try again. So on timeout happened. Presumably, we are in the init stage of the upgrade. So okay, yeah, we set stage to the init, go to stat. Set stage to stat, run the stat. Okay, like something happens, like we just say, okay, there is an error, and then presumably we will like retry on the next timeout. then we kind of like still flip stage to init, but you might or might not actually call binary open. And I think like, we call binary open when it is different. So in binary open, we flip our stage from init to source open and go and open the binary. Okay, we are in the source open. We get our file descriptor. And we start to read. Okay, now, okay, I don't understand why I was like confusing it. It seems like pretty straightforward, like, open, read, etc. So we want to read from our file descriptor into our buffer from the offset. And like, we nicely have the same offset for the buffer and for the file because we know that the file and the buffer are the same size. Okay, so then we see how much we read. We advanced our offset. We actually, man, there should be, okay, we advanced our offset. We assert that, okay. This doesn't matter. We don't worry about file actually being longer than the buffer because, I mean, we only care that the checksum verifies. Okay, so if we reached the end of the file, we go and upgrade our target. Okay, so I think, okay, what is source buffer, target buffer? Source buffer. Oh, okay, yeah, so source buffer is actual buffer, but target buffer is like a file in memory, which is backed by memory on Linux, but that memory is like memory map. So I think that's it. I think like, in the source buffer, like we have like whatever bytes we've read, and they might be completely invalid if like, file was only partially copied by the operator. But in the target buffer, I think we want to maintain the invariant that whatever is in the target buffer, it always is like fully valid binary, which we can execute from. Okay. We go and we try to parse offsets. And this may fail because we don't guarantee that the file, like the bytes are actually valid, but that should be fine. Okay, then we check if the binary, which is on disk, actually has code for our architecture. Okay. Then we go and fetch our multi-version header, which again needs to carefully deal with untrusted binaries. So this is again like universal binaries, which we are ignoring for now. Then we go and checksum our entire source buffer. But shouldn't we? Okay, where are we zeroing out the header? Oh, okay, it's right here. Okay, and that's why you don't do ls, because I'm like saying where are we like zero like the beginning of a source buffer? Well, this is source buffer header, but it's kind of like not obvious that it's like literally the same variable. So okay, we zero this thing out, now we compute the checksum. And if the checksum matches, then okay, then this is fine. And we know that, hey, this is indeed fully valid binary that we have read from disk. Okay, now we restore the header. Again, macOS thing. And then we want to upgrade our releases list. If what? Okay, so release on disk includes the release we are running. That makes sense. The existing release is bundled of any versions newer than the current is a subset of the new advertisable releases. Aha, so here I think we want to backtrack. So if operator dropped a binary and it contains version 3, and then it dropped a new binary again, and it doesn't contain version 3, we actually don't want to change our target. We want to keep the binary with that thing. Okay, let's see. So this is more complicated than it needs to be. Because Z has 4 expressions. Okay, now this is much better. Advertisable is forward superset. Okay, I think this again can be simplified. Let's see. So we want to check that every release bundled is in the new releases. Okay, if the release is older than what you are currently running, it doesn't matter. If it contains the release, again, we go forward. If it doesn't contain the release, then we break out of the outer loop with false. Otherwise, we just return true. Okay, this is nicer. For release bundled. Okay. It's really okay. Like, yeah, well, we are sort of missing contains, but I mean, okay, what is this? Was release list. Release list is just bounded array, and that kind of like means that we cannot write contains here. But yeah, that's why you shouldn't use bounded arrays. We should have just like open coded this. Okay. Okay. It feels like the soul could be like really simplified. Like why we even need to break this if we can just like check this here. So break else. Okay, running version is not included. Okay, and then maybe even here. Okay, and then here we say if we have a release which is not there, then we include not superset again, and then we don't need this, and we don't need this variable, and it all gets much simpler. Okay. Now this one I don't really like. I mean, that's like braces. Let's add braces. Similar here. Okay. So we log all the new release bundled. Same time, like, do we really need this line? Like, we don't really need this line. Okay. Now we say hey, this could be just an assignment. Okay, now we go and override file, and we don't truncate it. You see, I think there's another bug, because like our new source buffer might be smaller Can we have set and pause? What is set and pause? Shrinks or expands the file. So we should set this to source buffer.len. Okay, I guess, again, because you could just concatenate two files, there shouldn't be any problems with there being extra data after the end of a file, but better to fix this. Okay, and then we say, okay, now our target has header, body offset, body size, and we are ready. Okay, aha. So this is the key assignment, because this makes our releases visible in the replica and causes us to advertise. So after we've done all this thing, like we kind of like have atomically updated release bundle. I mean, atomically, there are no threads here. Atomically means without like any asynchronous operation. So while we are running this code, replica cannot run. And actually that makes me feel like this might be wrong, in a sense that, like, you know, this is like 10 megabytes of memory copy. So potentially this might be quite slow, or even this checksum. Haha. So this checksum is actually the largest checksum we ever have in Tagebeetle, because usually like our blocks are 0.5 megabyte, our messages are 1 megabyte. But here we do compute the checksum over the entire file. So this potentially might cause some nasty CPU stall. Okay, let's hope that we don't pull this too often. And anyway, it doesn't matter, because we only do this if stat tells us that the file was updated. So it probably is fine. Like there is going to be like a small stall when you actually do upgrade the binary, but well, kind of like you have to stomach it. But this one I think is like genuine bug. Okay, when we do open, well, okay, maybe this is intentional and we always make this like maximum size. Well, okay, then this is fine, but probably warrants a comment. Okay, so we now see the code which like updates a file, which is, I mean, just essentially a very simple pull and loop. We start a file. If it is new, we read it. Then we verify the checksums. Then we verify that it is actually a smart thing to do to upgrade to this new file. That is, it contains our own version, and it contains any version that was previously advertised. And then we start advertising it. So at some point later, the protocol will tell us here, actually go and execute the release. So let's see how that is going to work. Okay, we have our multi-version, and we go through release bundled, and if it contains, if it doesn't contain our release, then we say, okay, this is bug, like we cannot upgrade to something which we do not have. Then if we are Windows, why are we deleting replica? Well, I guess what we want to do maybe is what we want to free memory. So then we start a new process on Windows. We actually don't have to like use twice as much memory, which is actually a good reason for why we actually should care about memory the allocation. Okay. And then we have release exec or exec current if we want to upgrade. So, okay. Remember that like the latest version is slightly different. So all target-bit, like when you start target-bit binary, it starts in the latest version. And everything else is packed through special magic in ELF. So I think these are the two cases. This is like special magic through ELF and then the current. Okay, let's see release exec. We go and check that, kind of like just a sanity check that, okay, the binary is still like the same binary which we've started with. Okay, so we find our release. offset, then we reuse the source buffer. Is it correct to reuse the source buffer here? Can someone be? Okay. Okay, we do insert that timeout isn't ready, but like, how can we assert this? Start timeout start. Timeout stop. Okay, I don't get it. Why are we sure the timeout isn't taken here? It could be taken. Well, okay, maybe I missed this code, but that's another thing to think about. Okay, so anyway, we copied this into the source buffer. We read all. Okay. Then we write into the target buffer just the subset. So normally in the target buffer, we have like the entire multiversion binary. Now we actually write just the relevant slice here. Okay, yeah, that's okay. That's why we didn't need truncate at the previous point, because we actually didn't care. Like we weren't executing that file directly. We were like using it just like as a memory for multiversion. Okay, we truncate. We verify the checksum that like we actually are going to execute the file we want to execute, and then we execute. So on Linux, we execute using this in-memory file descriptor, like that's like in-memory file, which is quite cute. On Windows and Mac, we like have to re-execute from this target path, like the actual file in the GMP directory. Okay, and on macOS we just exec, and that's simple. On Windows, I think we don't have exec. Yeah, so we actually have to start new process and then to kill our old process, which is a little bit more involved. Okay, but I think we've got it. Like, that's it. This is like elf parser, which I think we've kind of like looked a little bit in the multi-version build process. So, okay, let's call it a day then. What we've learned today. Well, we've learned like the path for upgrading. So to start from the beginning, the workflow here is that TargetBittle is running some current binary, like, running for a day, running for 3 days, running for 5 days, running for a week. Someone makes a new TargetBittle release. Operator places this new TargetBittle release in place over the old binary. At that point, the multi-version code, which we've just read, will notice that, hey, we have a new binary on disk, and we'll read this binary, and we'll verify the checksums. And if this new binary contains new versions, those new versions will be advertised as, hey, we have these versions by the consensus. When this happens to all the replicas and consensus protocol figures out that, hey, let's go and upgrade to this new version, we will go and extract a specific version from this bundle, write it either to in-memory file or to disk, and then execute it, restarting at this new version. And at that point, at the superblock, we'll see that, hey, this new version is what we should be running. Okay, so I guess that's it for today. And next week, what are we going to do next week? I feel like we covered, oh, no, we haven't covered Whopper. So probably next week we'll look at the testing of version upgrades in Whopper. And also, I feel like maybe there is like a couple of smaller things like macOS multi-version binaries, which we might want to look slightly closer at. Okay, see you next week at 5 p.m. UTC live on Twitch and then later on YouTube. Goodbye.